welcome to Tulln and welcome to this building. Here we are located in a building that is housing several institutes of the Austrian Institute of Technology and of the University for Natural Resources and Life Sciences. I myself, I'm belonging at first hand to AIT, Austrian Institute of Technology, but I'm also affiliated to the university. You see frequently these logos. It's short. It's the Boku University. That's short for the Natural Resources and Life Sciences. Then you have seen me at the program that I will give you two small overviews concerning what is going on with respect to biochar in Austria, and later on concerning our applications in soil remediation. Then I want to thank Kathleen very much for organizing this, also for coming to Tulln, so that you will see something. Also thanks to Rebecca, who has guided you from Vienna to Tulln, and she will tell you also later on something about her work, and she's also a very experienced biochar researcher. So first, starting about the role of biochar in Austria. I want to guide you a little bit concerning how the importance of biochar has been found, or its way also to Austria. You see, Austria is a not very large country in Europe. And what's the relation to biochar here? In fact, I want to start with one person who is a quite famous Austrian. He said, if the world perishes, come to Vienna. Everything happens 50 years later there. And sometimes with respect to certain technological advances, you sometimes have the idea that it may be right, but we also may ask ourselves, is this also right for biochar? And I would say, so just for those who don't know it, it's Gustav Mahler, composer and conductor, quite famous musician. And I would like to show you that in this respect he was not quite right, and Austria is not so far behind with respect to biochar research then. So in fact, those charcoal heaps are indeed very old inventions, that charcoal burning is a handcraft that's distributed in many parts of the world, wherever forests have existed. And so that was also, as Austria is a land covered by a rather large percentage of forest, it's still 47% of Austria is forest. And so in former times, before coal was introduced as energy source, this charcoal was indeed quite important. And if one considers, Vienna is here and the capital needed energy, and the energy was coming to a large part from wood and charcoal that was produced in this forested area that were on the practically eastern end of the Alps. And this charcoal that were produced in such burners as you saw before, sometimes then were even transported by wagons drawn by dogs till Vienna. And those who know Vienna, there is still the Kohlenmarkt existing in Austria, in Vienna, in the first district. So nearly in the center, and this is indeed one of the most expensive shopping malls today. So this coal, it's not coming from cabbage, it's coming from the charcoal that was sold there at the time. So it was important always there. So going on, what is going, how is nowadays the relation between biochar and Austria? So this Heckley bird is the arms of Herald for Austria. is it a happy relationship, a fraught one, or what is at all the relationships? If we start, let me start about what's the size of Austria with respect to all over the world. You think, well, 7.6 billion of people in the world, Austria 8.8 millions, so it's not much then more than 0.1%. If you're looking about the publication schedule, and if we ask the Web of Science, it was a very, very simple overview. I just use Biochar. Of course, you also could extend it by far and see where Austrian researchers were involved. Well, it were 1.3%, so indeed it seems that we are a little bit overrepresented. So something seems to be going on, and Austrians seem to have discovered that biochar exists then. And so I would say, with respect to biochar, this hypothesis of Gustav Mahler is not really well applicable, and it seems that something is going on with biochar in Austria. And so I want to give you a short overview, really short, because for the rest you have the other 3 days. What are the Austrian biochar researchers working about then? Also started to think about that if you consider what is being published, that's also coming only from the Web of Science. Where do you see the most publications then? And I made a very arbitrary grouping, I must admit, just to make it a little bit simpler. So you see about the half part of the publications are dealing with the characteristics of biochar, the properties and those properties that are important for absorption behavior. About 1/4 of the publications are dealing with the applications in agriculture. What could you do there? Well, then about 10 to 15% has to do with energy use, with the interactions with microorganisms, especially with soil microorganisms, has to do again with the interactions with soil, and one part, what you also could consider as agricultural applications concerning phytopathology applications or support or use as pesticide. Well, and if we combine these topics, so this arbitrary grouping concerning these publications that are coming from Austria or also from Austria, you see this distribution is quite rather similar. So in fact there don't seem to be large differences to that what is globally studied and what's important for global biochar research. So more or less the same topics have a similar importance in Austria. Now, where are those people working about then? And here you see a map of Austria with a lot of arrows pointing from the logos of the companies or institutions to where they are indeed located. So where we are at the moment, this is here. That's Tulln, where Boku University and AIT together are working. In Vienna, you have also other Boku site and University of Vienna site and the Academy of Sciences. So there are several other locations in Vienna, and you have then also several companies working about biochar. Kindorf will be then your next important part of the excursion, where you will see more of the Sonnenerde company and daughter companies then. But there also exist those companies that are working about gasification, from Tyrol coming, The fourth day will lead you there, where you see the Syncraft plant. But there are also companies, for example, existing in Upper Austria, working about the production of reactors, and Syncraft, for example, is located, Polytechnic, sorry, is about located here. So there are several groups working in biochar research, both from the basic research and applied research, and from the production side of reactors. Just one overview what is going directly on here. Rebecca will later on also tell you more about her work, but just to keep it quite short, what we have here on the side, this is the small Biochar reactor. So it's practically the miniaturized reactor of that what Gerhard Dunst can show you tomorrow for the lab scale. Then Rebecca also is working with a contigy to produce biochar, and the topics that we are working about have to do with pollutant absorption. That was what's important with respect to applications in soil remediation, interactions with the nitrogen metabolism, use of secondary resources for nutrients like phosphorus with biochar, and the citizen science work, where you see a nice example on the roll-up there on the left-hand corner. That's been a product of Rebecca's project. So just to go a little bit on for what you will also then see during the next days. Gerhard has established the first real larger reactor in Austria that is producing biochar commercially, and is also working with farmers about with field experiments and applications. More you will hear from him directly. There are also a new focus concerning the production of feed char, different products specialized for either farm animals or for pets. There you will hear more from Dominik Dunst. So the Syncraft plant in Stadl that you will also hear, that you will see then at first, it's not the Stadl plant, but from Syncraft, one of the plants, and they have several locations where they have established already something, and Marcel Huber will tell you more about that. So companies where we could not arrange a visit, because then you would have needed more days, but which are definitely interesting also is, for example, the reactor of NGE, that's the company in Upper Austria, where they are mainly focusing on multiple feedstock possibilities, especially the feedstock for using sewage sludge as feedstock, or the Polytechnic company, where Mr. Kane will be so nice then to tell us a little bit then about this also this afternoon, where they have built large reactors. Then a few words what has been going on concerning the legal side from Austria. You have mentioned about the quality standards coming from IBI and from the European Biochar Certificate. There's also an Austrian standard, the norm S2211, which is also which is describing in which way the production, the sampling should be done, and what are then the threshold values for pollutant loads. In fact, they are rather similar, near to the EBC guidelines, just perhaps with the difference that they are complying with the Austrian Compost Directive. And for example, even although the biochar is not yet on the white list for organic agriculture, these guide values are already positioned in that way that when biochar can be used for organic agriculture, because the guidance lines are in revision, then these threshold values would also fit to the other guidelines that have to be considered in organic agriculture. What we have also made, this was a special report on behalf of the Austrian Ministry, former times Austrian Ministry of Agriculture, now they are calling themselves Austrian Ministry of Sustainability and Tourism. But they have practically also, it's a brochure that's much thinner than a book, but and directed to the practical applications also for farmers, but nevertheless including also a kind of SWOT analysis, as you have heard it from Kathleen before, so that the people who want to apply biochar have a short practical overview about the potentials and limitations of biochar. And so you see that also the Austrian policy is aware of this topic and wants to keep itself up to date. So finally, I think we can say there seems to be a quite value relation between Austria and biochar. There are, I hope not to have forgotten too many colleagues and groups that are working about, but I'm at least aware of about 9 research groups and at least 5 companies in Austria that are working concerning biochar research and or production or reactor production. So you surely understand that for these few days that you have for the excursion, not all groups or hotspots of research can be attended. Well, that was from my side this first part of that what I wanted to give you as an overview. Are there any questions from your side?
Could you say a bit more about citizen participation?
The citizen science.
Yeah.
Well, Rebecca is the project leader of this project. And Rebecca, may I pass on the question to you?
Yeah, we have part of the science communication project, the citizen science element within it. If you go find Elizabeth Sixty, I mean, I think we encourage people to use biochar in a small experiment, and then we look at how biochar affects the water use efficiency of bean farms, looking at the C13 levels. It's more to get people sort of hands dirty, really. Interested in other people. Tens of people. Yeah, we get a lot of people visiting and a lot of people taking hits, or hundreds of people, I would say. But the actual return is very low. But that's very normal for citizen science. This year I think we've had lots of data.
It's still running, so we don't
Yeah, this year we've had lots of data.
Any further questions? So if not, then I would proceed according to our program. Another special topic where I will give you about an overview concerning biochar and the possible applications in soil remediations then. Well, in fact, you have heard so many possible applications for biochar. Can it do everything? Some people give the feeling, and that's not always then the best. So can one really say it's a kind of Swiss Army knife for all remediation problems? Or where are the limitations for the use of biochar? I'd like to give you a few examples and explain you when and why may it work well and when not. So just to give you an overview about this general topic of contaminated sites, what are general possibilities how to deal with contaminated sites, or which remediation techniques are available, and how does biochar fit into these different possibilities. And want to tell you a little bit about these binding mechanisms. On the one side for trace elements, heavy metals, or for organic pollutants. Show you some applications for these such remediation applications, and limitations, and how in future new techniques might be necessary or should be developed so that real remediation projects can be done in the real world. Well, so if we have a look, what is the importance of the topic of contaminated sites and how to deal with them in Austria? We can ask the Austrian registry that is led by the Environmental Protection Agency. And it will say us that about 69,000 potentially contaminated sites are existing. 1,900 of them have been confirmed that there may be something risky in the soil, and in 293 this confirmation has led to practically the public order that these sites really have to be remediated. And from these 293, about half of them already have been remediated, and the other half still has to be remediated by or is under processing. And if we are asking ourselves, how does it come that these contaminations have happened, we see quite different industry branches here given, contributing to different numbers of contaminations then. So you see that the branch with the most frequent occurrence of contaminations is from degreasing or from metal processing. So you can imagine that there are also those chlorinated hydrocarbons, for example, have played a role, or that also heavy metals are a side effect from the metal processing. Cleaning shops also a source for the chlorinated hydrocarbons. Storing, reloading, and chemical industry, gasworks with about PAH contaminations then as an after effect then. And if we have a look then at the chemical distribution of these contaminations, you see that the chlorinated hydrocarbons that are coming here from the top two branches are indeed leading contaminations. And mineral oil coming second, coming in from the processing or refinery of crude oil. Then heavy metals, polycyclic aromatics are then the next most frequent contaminates. This is the collection of others not mentioned here, BTX, phenols, cyanides. So that just to give you an idea, what should a biochar really be able to be helpful, either as immobilization or for degradation then. And if we are looking at the landscape, how you would work with remediated sites if you have to remediate it, there are those techniques that are dealing with the containment of those contaminants, so to prevent that they don't damage the environment or groundwater further, or that they are not taken up by plants. Or if you can degrade them or can really eliminate them. You have quite a lot of different techniques, but biochar belongs to this part of the remediation techniques where the stabilization or immobilization is the main topic. So this, it practically accepts that pollutants like heavy metals cannot degrade, they are existing, so let us try that they do not harm the environment, and let us prevent them from wandering to groundwater or taken up by the plants then. So whatever we are doing about this immobilization, so I come from this general distribution, from this general listing of different techniques to the immobilization as one of the special techniques where biochar has a special importance then. And so we see that the main objective is then mainly then to reduce these bioavailable fractions, because the available fraction is that what could contaminate groundwater, or where these pollutants could be taken up by the plants then. So this leaching and the translocation should be reduced then. You don't have only biochar as an option if you want to prevent this leaching or translocation. There are many different mineral materials then, like lime, cement, clay minerals that may bind these pollutants. There are organic resins available. There are such asphalt or bitumen binders available, which also have the role to bind all those contaminants and to prevent their translocation. This eco-landfill is one special technique, for example, where for old landfills, where about 1/3 of the material is a relatively cheap material, but given in large amount to produce a kind of cement-like cover that will also prevent the seeping of rainwater into the landfill that would otherwise produce much more seepage water into the groundwater. So among the biochar, there are among the different materials for these immobilizations, we have biochar as a carbonized biomass, but also then, of course, also activated charcoals and activated biochar may have special binding effects. Otherwise, there are those calcium additives then, or those slags, partly from incineration plants, waste incineration plants, or from metal processing, silicates, other organic not carbonized materials are possible, or you work with oxides that have the possibility to have bondings with the metals then. And as it frequently may be the best options, that you all frequently also have mixtures of contaminants. If you work with mixtures of additives, you may then deal also with quite different contaminations. So what is going on then in the soil if we have contaminants here shown as the M, that as standing here for the metal, that they could bind either then to the iron oxides as one important immobilization tool. Then we also have biochar. We have other organic, not carbonized products or clay minerals where from the soil solutions these contaminants may bind. And this way both the uptake by the plants and the leaching should be reduced. So effectively, we want to interrupt the path that usually would go from the soil via the soil pore water to the plant root, where then the plants could take up either the heavy metals or organics as long as they are small molecules. When there are immobilization agents like the biochar in the soil pore water, then less of these pollutants will reach the plant root. And of course, less can also move downwards to the direction of the groundwater. So there are chemical mechanisms, there are physical mechanisms. And as we Kathleen also told you, there are quite a wide range of biochars that can be produced with quite similar products, processing technologies, and it's quite important to know these characteristics of the biochar surfaces, because this determines then what are your surface groups. Or what are then the possibility for electrostatic interactions between the biochar that's produced from different feedstocks or at different temperatures. So if you can imagine, when we are coming then from biomass with cellulose and lignin as main compounds and are producing then sheets in the optimal case that are related to graphene, although it's not graphene, it's much more irregular, but with holes, with sometimes 5-ring instead of 6-ring compounds, but it is a graphene-like structure. And finally then we have here either then such functional groups, or we have then the negative surface charges where the cationic contaminants could easily bind there. In the case of the organic contaminants, these hydrophobic interactions are much more important, or the p-electron interactions are important. Frequently, those organic pollutants also have benzene rings as a compound, and these sigma electron, the p electrons that are characteristic then for the double binding in a 6-ring. This double binding consists of one sigma and one p electron orbital. They may overlap with these benzene rings that we have in these aromatic condensed carbon structures. That is what a biochar is made from. Also, this pore filling and other hydrogen bondings may also play a role. But these hydrophobic adsorptions and the PP interactions are most important and for the organic sorptions. Concerning the production possibilities and what are then the resulting properties of the biochar, one can use about as a crude rule of thumb that at higher temperatures more of those functional groups are being lost, but this biochar has then more aromatic condensed structures at the surface that are then more useful for these p-electron interactions that you have in the organic, for organic pollutants important. At a lower temperature you still keep more functional groups that might be useful then for the binding of cationic substances, for example. But this is indeed quite a crude rule of thumb that has to be always studied in detail, what the interactions of your target contaminant and your biochar really will be. What you also have to consider that there are many indirect mechanisms that play a role about the contaminant binding when you add biochar to the soil. You know, the pH of biochar is quite high, so this affects also the soil pH. It affects an acidic soil much more than if your soil is already neutral or high in pH then. But this has to do with the availability and the solubility of certain metals. Well, if we add a biochar at the surface, small, low molecular hydrocarbons may remain that contribute to the dissolved organic carbon load of the soil. And if you are dealing with metals that are easily forming complexes with these organic parts, then, for example, copper, that's quite fond of making complexes with organic matter, then you may even increase the ability to move for translocation of copper, for example. Considering phosphate, that's a topic especially for lead. If you have more phosphate in your soil or at the biochar, you may easily precipitate then lead as lead phosphate then. And finally, also the redox conditions are considerably changing, and depending on the metal, depending on the redox sensitivity of the contaminant, you also may affect this solubility. So finally, also the specific surface area has also to do with the pore formation that is then characteristic for the pyrolysis process, and that will contribute to the increase of the surface areas. I told you that especially heavy metals are by far not all or have the same binding ability to biochar. Unmodified biochar is a quite good sorbent for cationic metals, but for anionic elements, for those anionic elements, then there may even be an increase of the translocation of the metals, because a negative surface of the biochar will not readily bind an anionic element. So in this overview here, this dashed line would show if there would be no difference between a soil with or without biochar with respect to the available fraction of certain elemental contaminants. And here, when you see then the cationic elements, but also organic pollutants, but this has to do with the pp electron interactions, here you see that these are always then reduced with respect to bioavailability, but elements like arsenic or boron or molybdenum, they are occurring mainly as anions in the soil, and their translocation, their availability is increased considerably. So you must well know what is your contamination in the soil. One also, of course, has to consider when you use biochar in the soil that this sorption ability does not only apply to contaminations, but also to micronutrients, for example. And if you have a soil where certain micronutrients for plants may already be in deficiency, you must consider well that the sorption ability of the biochar may make this problem more severe than before. The other hand, anionic elements will be mobilized and taken up easier by the plants. So, but this is not nothing where you are defenseless or where nothing can be done. It is possible to build iron or magnesium or manganese bridges between this negative surface charge of the biochar, so that also anions may bind easier, or you may try to oxidize mildly the surface of the biochar to provide more functional groups then, or by organic acids then. And practically what you do with the activated charcoal, the same way of processing can also be done with biochar. So like the water vapor activation or strong acid or base activation, so that you are connecting the much higher sorption activity. And finally, the composites may also be quite well effective if you consider zeolites by themselves have already very interesting properties, and the production of such composites with zeolites may sometimes combine the benefits of both. So to come to a few examples concerning biochar applications then, what I don't want to just want to mention that, for example, in Germany, the Laterra project has produced quite interesting results. They are working with the remediation of former military areas, and several publications have been appeared in the Altlasten spectrum where this project has been combined. And I show you a few examples from projects that we have done here now following. One project had the task to remediate a soil that had mixed contamination of polycyclic aromatics plus heavy metals. So this contamination was composed of cadmium and zinc, and we have phenanthrene and pyrene in this respect as a spiked soil there, and we wanted to reduce the translocation to seepage water by constructing such microlysimeters where the seepage water was collected with the suction plate. So not a gravimetric but a suction plate lysimeter. And what we then finally saw, that the different treatments were consisting of different combinations of biochar and compost. And it was practically then the task to see what was the advantage of biochar, what was the advantage of compost, what did which, and there was also a modified biochar included there. And if you just focus on these green columns from the different treatments, so in fact in the end, after a long incubation time, the degradation that was mainly caused by these microorganisms coming from the compost was similar. But when we had the combination with biochar, apparently it was a little faster in those polycyclics where this degradation was slow enough so that you could follow that. Phenanthrene is the smaller pH with 3 rings only that was degraded so fast that there wasn't a difference there. Pyrene was a 4-ring compound, is degraded slower, so there we could find by the combination of biochar and compost here an enhancement of the degradation. Also concerning seepage water, so that at first was the concentration in the soil, total concentration, but also the translocation into the seepage water was reduced a little faster by this biochar plus compost application. Another example, the topic of copper contaminations in vineyard. Copper has been used as a fungicide in vineyards since nearly 150 years. or at a larger scale at least since 100 years, and in old traditional wine growing regions. Therefore you have quite a large problem of copper accumulations in the vineyard. And copper in the soil cannot be removed. It may be a disadvantage, especially for the green cover crops that are growing there, because this copper is in the layer of 20-30 centimeter, so not the layer where the vines are rooting, but where the green cover crops are rooting, and it may be a problem for them mainly. So we were also applying different compost biochar treatments there, and what we have seen that those treatments where biochar alone was applied, this indeed reduced the copper uptake. That was valid both for clover as also for raygrass. But if compost was included, no matter if compost alone or compost in combination with biochar, the mobility of copper was increased and the uptake of copper was higher than without all those treatments. So finally, we also were looking at different fractions of copper in the soil, and we have seen that the available fraction may, so this was a lab experiment, and also in the lab we saw this increase of copper availability if you were working with combination treatments of compost plus biochar, and only if you were looking at the fraction of the ionic copper, of the copper 2+. Here we could see that a reduction, these were modified biochars, were quite effective. So biochar had a desired effect, but not on all available copper, but only on a small fraction, because you must consider that only a few % of the complete copper in soil is this ionic copper. So you can find, you reduce the ionic copper, but 95% of the copper is not affected by this treatment. So it's not that what a farmer really has use of. Coming to that, what if you find applications that are useful in the future, one must be aware that contaminations usually do not occur only in the top layer of soil, but may occur in many meter depths of soil. And an application only can work if you get the contaminants and the biochar into contact. So this then would indeed need then enhanced engineering techniques like deep drilling and a combination of these drilling rods with nozzles, so to put in a slurry of biochar, for example, into the soil, where you then can reach meters of up to 20 meters, where you combine then the biochar slurry with the soil, and then those binding effects that I showed you before between contaminants and biochar may become effective. Or other possibilities how such deep soil mixing might work. Here these are turning and screwing down, and in parallel they are spraying this slurry of biochar into the soil, and when they are removed, then they keep there. You have then this slurry plus soil mixture down there. So this we know that would work from principle, but not yet in real-world applications, just as a pilot experiment. So coming back to my first question, or about the usability of the biochar, in how far you can compare it with a Swiss Army knife, I would say yes, but the comparison is always not 100% perfect, because there are also many different Swiss Army knives. Do you want to have this one or that one? And even if you have one, you might need to modify it. So in fact, think your biochar, then you may have the optimized biochar for your specific problem in your soil. So finally, to come just a short overview, what I wanted to tell you that there are different remediation techniques. Immobilization of contaminants is one of them, and biochar is one of different agents that may be effective for the stabilization of pollutants. So we mainly dealing with heavy metals or with PAHs, although others may also work well, but there you always have to try that first at lab scale if it works. I gave you an overview about these bonding mechanisms, direct, indirect effects, differences for metals and for organics. Then I showed you some possibilities for these modification possibilities, and that you cannot always work with small Baker classes. In real world, you have to deal with tons and deep soil mixing that you really can be effective in remediation. Well, this was this overview about this application of biochar for soil remediation. Thanks for giving me so much time, although lunch break has always started. Nevertheless, I'm still here to answer any questions. Please, yeah.
So, do you think if a particular biochar is good at immobilizing a particular metal in soils, it would also be good at harvesting it from effluent water?
Well, if it is effective in soil, it is effective because it is absorbing it from the soil pore water. So you have water included there. It's coming from the hydrous phase then. So in fact to produce so a kind of cartouche filters, for example, with biochar in a similar way as they are commercially available, filled with activated charcoal, these may well be possible and may work.
Has there been any work done on measuring biochar's absorption of firefighting chemicals, so PFAS in particular?
I'm aware of some work in Norway where something is going on concerning firefighting training places or something like that, and where apparently it's not yet as good as the activated charcoal. But that's just because there are some unspecified biochar that has not been modified and not optimized for this task has been tested. If one would develop that, I could well imagine that the absorption might become more similar like the activated charcoal. Please.
I wonder if you've heard of any work with radioactive materials associated with Chernobyl or Fukushima.
Sorry, I did not get this.
I'm wondering, I think biochar would receive great publicity if it was appropriate for nuclear accidents.
Yeah, but also concerning radionuclides, you have to consider, are they occurring as cations or anions then? So it's indeed important what's in your soil there. So there are some regions in Eastern Europe where you have sometimes large regions with quite low, but still still existing contaminations with radionuclides, and especially for large regions, though the biochar application may be more useful than for small hotspots. So whenever you know where is your hotspot, where the plume is coming from, you better remediate at first the hotspot, and then for the larger area with low remediation, with low contaminations, you may think of such techniques like biochar immobilization.
But there have been tests with biochar and radio impact.
Not we here, but some project partners in Slovakia have done this. I can give you a connection to them. Susanne, please.
Yeah, did you make some cost comparison up to now to other possibility or possible materials concerning zeolites, because they are perhaps much more cheaper and have the same effects combined with compost, or was it?
Yeah, but well, compost definitely is the cheapest of materials, but the absorption potential is always lower than biochar. And
Also with
and
zeolites.
and what you also have to consider the time scale.
Yeah.
So, well, for zeolites, the binding may indeed be long term, also with biochar. But concerning composts, you have a life duration of, well, perhaps 5 to 10 years till most of it is mineralized again, and then also that what had already been sorbed would be released again then. Concerning the zeolites, it depends if you are using natural sources of zeolites, that would be cheapest, but they probably also would need modification if you want to optimize it for your specific purpose. If you're using synthetic zeolites, I cannot imagine that you would be much cheaper than biochar. Yeah, please.
Gerhard, thanks. We've tested biochar for metal absorption, in particular, copper was one metal of interest, and found very high absorption rates and high retention rates when we tried to basically get it to desorb. But in your study, it looked like you were focused instead on the bioavailability and the biouptake from the plants. So if you were doing it not in a way to test the uptake, but rather just to test, if you will, test it for its ability to hold and retain the copper, did you look at those two separate properties or only at uptake?
Well, in this respect, we were looking at the uptake only. Was not long enough this project that we could analyze then the desorption again. But in fact, it is a established field experiment where we are intending to resample the soils from that and take the soil samples to analyze the desorption from these old experiments. That's something that we want to do in the next years then.
Is the concern, for example, if you were doing, let's say, remediation of a copper mine site, and you try to use biochar for that, the copper runaway might get uptaken by the plants that then grow in that soil subsequently, and then when those plants degrade, they would re-release the copper? Is that the concern in a way?
Well, if you're dealing with mine tailings, I think that the main question frequently will be, would there grow any plants at all? Because frequently the soils are then so acidic and so low in organic carbon that the soil remains bare. And if you even can grow any plants, it will already be an advantage. But I wouldn't yet dare to say that you can harvest and use the plants. But if you want to use the plants from any contaminated sites for concerning phytoextraction, well, all those methods where you use the plant material energetically and you concentrate then the heavy metals in the ash then it's already an advantage if you have the lower ash volume with higher metal concentrations than the whole plant. Yes, please.
In your analysis of the copper site in the vineyard, did you investigate the microbial community composition?
Yes, yeah, there was a large part and work package concerning the effects on microbial composition and activity of enzymes. We just can say that there were changes in the composition, but one cannot say that they were either, it was not clear that they were beneficial or at a disadvantage. We just saw that there are changes. Also with respect to the activity of certain soil enzymes. But we couldn't say that it's really good or something that's really bad. There are just changes, but one cannot say if it's not a matter of usual adaptation in soil. Any questions more?
Have you done any work looking at if you take logs or woody material that's contaminated with copper arsenic and then convert that into a char, whether the arsenic, given its anionic properties, ends up becoming more bioavailable, but the copper ends up being retained?
Well, we did not test such materials, but I can imagine because the arsenic usually occurs as anion. So you need to modify the biochar, otherwise you surely will mobilize the arsenic then, no matter from which source, if either geologically or from a former application or contamination then. Yes, please.
The Chernobyl question, I take a handful of that soil, that radiated soil, and then I've got another handful that's got biochar in it. Is this one receiving less radiation? Is my hand receiving less radiation?
Radiation from you mean from the atmosphere?
No, so this contaminated soil.
Yeah.
So Chernobyl is the example.
Radioactive contaminated soil. If you can absorb a little bit of radiation, I think this is the question, right?
Yes.
Can you absorb radiation with biochar?
Is it like lead that stops?
Well, I think that not the radiation itself is so much reduced, but the mobility of the radionuclides in the soil pore water that might be translocated to the groundwater or to surface water during soil erosion. This might be reduced.
Sticky, does it, the biochar?
Yeah, but there are results that you improve the soil aggregate stability. Bruno, please.
But to answer your question, it's the other way around. If I have here biochar, here soil, so in the center you have radioactive uranium, the absorption with soil will be much higher than with biochar of the radiation.
Because of the specific density differences.
The absorption in the soil.
Your specific question was related to the absorption of radioactivity.
By the human hand.
Yes.
Yeah.
And if you have a soil, or if you hide in a soil if there is a nuclear fallout, then the soil is a good thing because soil has minerals which highly absorb any kind of radioactivity better than carbon, which is light. But this is not the case here. It's a different mechanism. And in the same way, I mean, if he's talking about radioactivity and remediation, I mean, it's not about remediation of radioactivity. It's about remediation of the chemical elements and the physical chemical state of the elements which are in the soil. So it's completely different things.
Thank you. Right. Thanks, Jan. Kathleen?
I just want to say one thing on the phytoremediation thing. Back here on the table, I put a couple of samples of building materials that were sent to me by an environmental engineer from Canada who is phytoremediating landfill leachate. and then he's carbonizing the fast-growing trees, but he knew the metals were still contained in the biochar, so he was looking for different things to do with the biochar to immobilize it. So he's come up with these bricks and this drywall. So you might want to just take a look at that, because I think that's a really clever use for that kind of biochar.
Okay. Any questions more? Or it's time then for lunch break, I would suppose.